Okay, so how is everyone today? Good? All right. Today's the 14th. So right now we're in section, we're just exiting section 7.5. And section 7.5 in the textbook is called Strategy for Integration, but again, I'm taking a firm stand against calling it thus, and I'll refer to it as anti-differentiation. Because when the book says, in that title, it says strategy for integration, and it doesn't mean that. It actually, in its own terms. So like the statement, the title is wrong in its own terms, because the title really should properly be strategy for indefinite integration, according to the book's terms. And but I just won't even. So I'll keep referring to it as strategy for anti-differentiation. So here's the deal. Again, I made kind of a silly joke last time. I said something like, you know, like what rope is. You can imagine what rope is. And then concerning a rope, is it easier to pull a rope or to push a rope? It's easier to pull a rope. Okay, just because of the dynamics of the way the thing is made. Now, if you had a stick, if it were a stick, it is, you know, arguably less difficult to push a stick. You can surely pull a stick. But concerning rope, it's so, you know, it's hard to push a rope. And in differentiation and anti-differentiation, because of their inverse relationship, it is a fact that differentiation is easy in the same kind of sense that pulling a rope is easy, and anti-differentiation is difficult in the sense that pushing a rope is difficult. You can do it in principle, right? If the rope is stiff enough, if the piece of rope is short enough, if it's going downhill, you know, you can make it work. But it requires a lot of techniques depending on the situation. So that's why, you know, I can summarize all the differentiation rules that you need to know on one page easily. I can just summarize them. But concerning the anti-differentiation rules, there's so many of them. There's so many of them, and they only apply to their very specific situations. And the only way to achieve success, essentially, is to just do as many of these problems as you can, so that when you're faced with a new one on a quiz or an exam, you can say, "Oh yeah, I recognize this. I remember last week or last month or when I was going through this and I faced one just like this, and now I remember what to do." That's how it is. And I promised you if I could make it better, I promise you I would. But it's just not possible. All right. So let's have some examples of doing this. So we'll do a couple of examples, and then we'll just have to move to the next section. So if you see one that looks like this, again, we're not going to take the time to fully do all of these, but just to describe how we would proceed. So if you're faced with this one, okay, then what would you do? You'd have to do long division. And notably, long division, that's not even a calculus thing. That's a completely algebraic thing. What is your signal that you need to do this long division? Mm-hmm. So, notably, you note, this is a rational function. And remember that the meaning of rational function is that it is a function that is the ratio of two polynomials. And then once you've established that something is a rational function, your very first question, if it's an anti-differentiation question, the very first thing you need to ask is it proper? So is this specific one, is it proper? It is not. And because it is not proper, you will do long division. So in a sense, long division has two inputs. The numerator is one of the inputs. The denominator is one of the inputs. Okay, they are called the dividend and the divisor, respectively. Long division has two outputs, and they're both, and it's two more polynomials. One of the outputs is called the quotient, and the other one the remainder. So the notable thing about it, in the first place, is that long division is unique. Like when you do it, you always get the same thing, right? There's no randomness to it. And furthermore, the remainder will have the property that its degree will be strictly less than the divisor. So the remainder, whatever it is, has to have degree less than 3. Less than 3. Not less or equal, but less than. So the remainder could be degree 2, degree 1, or even degree 0. Okay, which would you know, if it's degree 0, that would be interesting. And if it was in fact exactly 0, then that would mean that in fact that this thing is a proper divisor of that, in the same way that 5 is a proper divisor of 20. All right. So because it's a rational function, you ask the question, is it proper? Proper? The answer is no, and therefore you long divide. To find q of x, which is to say quotient of x, which is to say the quotient and the remainder. So supposing that you find those, whatever they may be, that's telling you that x to 5 plus 1 would be this divisor. Multiplied by the quotient plus the remainder. So that's what long division is saying. These the inputs. Those the outputs. You find those two green things. And then, of course, as written, this equation does not include that thing that we want to anti-differentiate, but how do we get that thing from this equation? Right. So that you get this. Over that. And so what the conclusion of this purely algebraic thing is that, well, instead of anti-differentiating what you gave me, I'm going to perform some rigorous algebraic manipulations to say that because this thing is equivalent to that thing, I'm not going to anti-differentiate that, I'm going to anti-differentiate that instead. And that's an improvement because q of x is a polynomial and it's easy to anti-differentiate that. And then this is an improvement because now this thing is a proper rational function, meaning that the degree of r is less than 3. All right, so there you would have it. So now it might be the case, you know, I'm not at all saying it would be the case. I'm not at all saying that it is the case, but I'm saying suppose it is the case. Suppose you do that, and r of x ends up being exactly equal to 3x squared minus 6x minus 10. I'm sure that that's not true. I'm sure it's not. I'm just saying suppose that that's the case. Then that would mean that this term, okay, we'd want to anti-differentiate that term, and it would look like this. Okay, and I'm ignoring the q because that's easy. That's a polynomial. So suppose that we get to this to this position. Well, again, we'd say, it's a rational function. That's nice. Is it proper? Yes, it's proper because that, I mean, that's what we did all that work for. And then, so that means that we don't need to do another long division, and we need to ask ourselves, well, how would we proceed now? You sub it? What does that mean? What do you mean, I guess? Right. So notice that it has this nice relationship, okay, that concerning the polynomial in the denominator, if you differentiate it, you get the polynomial in the numerator, right? So what I want you to observe is that, you know, algebraically, you could reckon it like this. You could say that it looks like 1 over x cubed minus 3x squared minus 10x, and then multiplied by 3x squared minus 6x minus 10 dx. And what I want you to observe from this situation is that here I've got red thing, okay, red thing, and then if I differentiate red thing, then I get green thing dx. And what I want you to hear is that because you have an expression that looks like that and then multiplied by that thing multiplied by derivative of same thing, that I want it to be in your mind screaming loud that that sounds like chain rule was here. Okay, because the chain rule says that for example, if you want to differentiate just for example, the derivative of x cubed, say. Well, that'd be 3x squared, right? That's just the power rule. But if I say the derivative of, say, w cubed, so that x and w are not the same. See, x and x are the same there, but x and w are not the same there. So what w represents what I'm doing to x before I cube it. So like, you know, maybe I turn it on its side or turn it around or multiply it by 10. I don't know what I'm doing. You know, just w is just a placeholder for whatever I'm doing to x before I cube it. And then I compute derivative. Well, again, because of the power rule, this would be 3w squared. But now I also have to encode whatever it was that I was, you know, how does whatever it was that I did to x before I cubed it, how does that affect the derivative? Well, now you have to multiply by the derivative of w with respect to x. That's the chain rule. So when you see something that looks like, that looks like this thing, expression in w multiplied by the derivative of w, that's chain rule. When you see expression red thing multiplied by derivative of red thing, chain rule. It's screaming chain rule to you. And then the name of, you know, because antiderivative is opposite of derivative, when, you know, for every rule there's a corresponding anti-rule. What's the anti-chain rule? Variable differential substitution. Okay, so the fact that this is screaming chain rule means that it's also screaming substitution. Good. So then I'll do the substitution that was suggested. Uh, 10x. And then du would be exactly that. Would be 3x squared minus 6x minus 10. Okay, so now, what's wrong with what I have written here? Now, there's no dx over there. So here's the deal: is that when you write such a thing, however many d thingies are on the left side, there've got to be that many on the right hand side. That's what makes them the same kind of thing. So this kind of statement, it's not exactly clear. It's hard from the point of view of calculus at the 2000 level to understand exactly how wrong this is, but it's like utterly wrong. Okay, like sort of like equating an apple with like a picture of an apple. Okay, they're related, surely, but not the same. Good. So then doing that and making that substitution, the antiderivative becomes, well, 1 over u, then what? du. So every time you do any major thing, like a substitution or a major algebraic step or something like that, you should always go back and consider. So here we've majorly changed something. Is that one of the exit doors? Is 1 over u du one of the exit doors? It is, right? It's door number 2. Okay, now it may surprise you, maybe not. So this is, door number 2. So the answer is logarithm absolute u plus a constant. And then that can't be the answer because the question was phrased in x, so the answer must be phrased in x. So it would be this, x, what was it? Cubed minus 3x squared minus 10x plus c. All right? So now I think it might help to show you how a problem is made. Okay? So because of the trickiness of antiderivatives, in the sense that it's hard to push a rope, every antiderivative has to be, in a sense, made to work. So that we give you a question that's going to work. Because if we just randomly choose something, it's virtually certain you can't do it. So we've got to engineer the questions before we give them to you so that they work. All right. So here we go. Concerning these doors here, the way you make a question is you say, okay, I'm going to choose a door. I choose door number 6. Okay, so antiderivative of cosine. So this is hidden. So this is me back in my office, and you can't see this. Okay, so here's the one that I'm going to use. So cosine theta d theta. All right. Now, well, I can't give you that question. That would be too simple. So I need to make it more entertaining somehow. All right. So then I'll say that I'll write that theta is in fact equal to something curious, like the square root of 5t squared plus 8. I don't know, like that. Suppose I'm just writing something down there. And then if that's the case, then d theta would be 1 over 2 multiplied by the square root of 5t squared plus 8, because if this were exactly square root of t, it would be 1 over 2 square root t. And then for the chain rule, I need to multiply by the derivative of 5t squared plus 8, which is 10t. And then to make the form number correct on both sides, I have to write dt. All right. So then I say, okay, well, then if that's the case, then it would look like this. Cosine of this monstrosity here that's what theta was. And then now I write this. Wait a second. Again, I'm not solving an exercise. If it wasn't clear what I'm saying, I'm telling you that I'm making an exercise. This is the hidden step that you don't see me do back in my office. So now I'm going to take this, and I'm going to mess around with it a little bit in ways that don't make it impossible to go back. So I see 10 and 2. Those are constants. I'll just be rid of them. I'll just get rid of them, and I'll choose some other constant that I like that might muddy the waters a little bit. I'll write pi. I'll write antiderivative of pi multiplied by the cosine of the square root of 5t squared plus 8, like that, And then I said I'm going to, this is not really equal, because I'm messing around with stuff now in ways that make it to where we still have a problem that works. And then I'll change that t to a t squared right there, which would make the problem basically impossible to fix. But then I'll put another t down here, and in the hopes that you'll notice that you can make a cancellation. So I accounted for that one, and that one, and that one, and that one. So dt now. All right, so here's the question. So you can't see any of that. So the question is, please calculate the antiderivative of pi multiplied by the cosine of, now I'll use some other character like y, square root of 5y squared plus 8, like that, and then multiplied by y squared, all divided by y multiplied by the square root of 5y squared plus 8, and then all of that against dy. And then there's a question. I made one for you. Now, how, as an instructor, I just made this. How can I be sure that when you exit this problem, there is a door that you can exit through? Because I started with it, right? The end was, I determined the end at the beginning of the construction of this exercise. All of these exercises are decided that way. Is that, I just say, well, I have to make 8 questions. Okay, on this one, they're going to exit through door number 14. And on that one, they're going to exit through whatever. And then I just muck around with it a little bit. That's the way all of these work. Okay, now up to some constants, you won't exit exactly through this door because I played with the constants. There'll be a constant times that door is what it will really be. So is it clear how it works? Good. Next thing. So we've got antiderivatives, we've got integrals. So remember that, so this is section 7. We're in a new section now, section 7.8. It is called improper integrals. So improper is linguistically is an adjective, and that means that I could say something like like red integrals, or whatever, or like tall integrals. So if I say, what I want you to observe here is that if we're calling these improper integrals, I hope that you have a sudden shocked question like, well, then what's a proper integral? If we're suddenly talking about improper ones, then what could possibly be meant by proper ones? Okay, fine. Before I address that question, I just want to let that simmer for a second. Is that remember that we have 2 ideas. Is that on the one hand we have derivative. So we have derivative f of x. You put that into the derivative machine, and out comes the derivative. Okay, like that. And then if you run that machine in the reverse direction, so the input is a function, the output is a function, and if you run that machine in the reverse direction, what do we call that machine? Antiderivative. Okay? So then if you run it like this, that direction, then for reasons historical, it changes its name and its appearance, and it looks like that. So running it that way is called derivative. Running it that way is called antiderivative. Okay, this is going that way is very easy. Like there's just a very short list of rules. It's always going to work. Going the other way is complicated. Now, separate and apart from that. Well, back up just slightly. Derivative has its geometric interpretation is that if you have a function and you consider its graph like that, and then you select a point on that graph, like that point right there. If the graph of that function is nice, in the sense that if you can imagine standing on the green point and being exceptionally small, you know, zoom in super, super far, then you get close enough and that red will look flat. Understand when I mean flat, I mean like a line. I don't mean horizontal. Okay? The floor is flat. The wall is flat. The floor is horizontal. The wall is not. So you zoom in close enough, then it looks flat. What derivative is telling you geometrically is that if you were at that point there, and you zoomed in close enough, and it is the case that the world is flat, then the derivative evaluated at that point tells you the slope of that line. That's what it's telling you. Okay, now as a separate question, you can say, this is a rectangle. Beautiful. Then you can measure its base and its height, and say rectangles have area, and it's the product of their bases and height. And then you can say, well, here's a shape. So I could, call this like x0 and x1, something like that. Here's a shape that is the plot of a graph, plot of a function there. And if that's the x-axis, that means some of the time the function has positive outputs, sometimes it has negative outputs. And then you can consider this shape right here. Okay, now that is a shape and it has an area. And it's common enough to have a name, right? It's rectangle. And there's other shapes that are so common that they have names like circles and what have you. But here's a shape, and I think we can all agree that it has an area, but it doesn't have a name, right? This is not something that is among the named shapes. Nevertheless, it has an area. And the way that you can calculate the area is you can imagine the following idea. You can say, well, imagine that the only thing I know about area is rectangles. Then you can take this and you can cut it into little rectangles. So suppose I cut it into rectangles, and I choose the tallest rectangles that fit under the curve like that. So always within. And for reasons that we said previously, we'll reckon that area to be positive because you go first with the horizontal direction and then with the vertical direction. So we'll reckon these rectangles as having positive area. And then we'll use these rectangles also, something like this, and we'll reckon these ones to have negative area. And then doing this, we can come up with an estimate for the signed area of this shape, but it's just an estimate because you can see, like, I left out those little bits there, little bits. So it's not perfect. It's just an estimate. Now I drew what, like 10 rectangles there. So we could make the estimate better by, instead of using 10 rectangles, we could use 20. Or instead of 20, maybe 20 million. But for any finite number of rectangles, it's an estimate. Now, the math idea, the calculus idea is that, well, what if we let the number of rectangles become infinite? What if we just say we're just going to use infinitely many? We're going to go way past 20 million, even 20 million, way past all that to infinite. That idea is called integral. So integral is cutting a shape up into infinitely many infinitesimal rectangles, measuring the area of each one of those rectangles and adding them all up. That's what integral is, geometrically. Derivative is slope of tangent line. Integral is finding signed area by cutting into rectangles and summing. So these seem like starkly different ideas, but the super surprising thing is that, in fact, these two things are intimately related. And what's the name of their intimate relationship? Starts with F. And it ends with fundamental theorem of calculus. Yeah, that one. Yeah, that one. So the FTC says, when you cut a shape into signed rectangles and add up their areas, it doesn't have to have an area. There doesn't need to be one, right? Because there's shapes that don't have areas. But supposing it does have an area, what it's saying is that if you know that, and I'll write it in the way that your book writes it, suppose that we know the derivative of big F is little f. Suppose that that we know this, so given that, okay, and that this exists. So what we're saying is that we've got two functions such that when you differentiate big F, you get little f, and furthermore, we know that that integral exists. Then on the one hand, you could use the definition and cut the shape, the signed shape, the shape defined by this, and cut its signed area into pieces and into rectangles, and then proceed to infinitely many rectangles. You could do that. That'd be fine. That's the definition. But you don't need to do that. The fundamental theorem of calculus is saying that, in fact, instead of doing all that very tedious stuff, you can, instead of evaluating little f at infinitely many points, you can just evaluate big F at 2 points. And that's incredible. Now, here's the deal that I want to stress for you, is that what does it mean for an integral to exist? Okay, so you've got to look carefully at the definitions, because there's something that my experience tells me that when I get to this section, essentially all of you have overlooked. There's something slippery about the definition. Okay, so the slippery bit is that when you are defining an integral, in the definition of integral, you say, let f be bounded on a to b. Let f be bounded on a to b. Okay, so that statement is in the definition of integral. So if I ask you something about this, if I say, something like integrate has an e, integrate f of x equal 1 over x on, say, 0 to 1. Okay, and I have to write open 0 there, because you can't plug in 0, right? If you look at the picture looks like this. So here's 1, and here's 0. And then 1 over x, that's the hyperbola, right? The thing, that goes crazy near the origin. It looks like this. So the area, if anything, okay, must mean all of the area under the red between 0 and 1. So that means that we'd be talking about this. And so do you observe that, in fact, that goes all the way up infinitely far? So what I'm telling you is that by definition, you can't do this. It's not part of the definition of integral, because the function is not bounded, and so by definition, it's not even permissible that you should proceed. Similarly, if I make a similar statement, I could say, well, what about if we say integrate g of x is again 1 over x, same function. But now I'm going to select an interval on which it's bounded. So I'll say something like, on half to infinity. Now that shape, whatever it is, if it makes any sense whatsoever, then that would mean something like this. So there's that, and then here's half. And then again, the red is the hyperbola. And what I want you to observe is that that shape, if anything, means this And how far to the right does it go? Infinitely far. So what I want you to observe is that, in a sense, concerning these two examples I've given you, here's a shape that is not vertically bounded. Okay, and here's another shape that's not horizontally bounded. But a way to say either one of those is that notice for both of these shapes, there is not a circle of any size such that you could fit that shape in the circle. Right? You can imagine any kind of weird shape that you can imagine, like Britain, okay? You know, like the outline of Britain, okay? It's a big place. But can you draw a circle around it? Yeah, you can. But this shape, it's not possible to draw a circle around it. Now, this, you can't even get started using the fundamental theorem on this, because you can't even integrate it by definition, because this statement, let f be bounded on a to b, as part of the definition of integral, and this isn't bounded, so you can't do it. Furthermore, you can't do this one either, because this statement, let f be bounded on closed interval a to b, so you can't do this one either. Strictly speaking, this doesn't make sense, because this is a closed and bounded interval. That's where integrals are defined, but my request is not a closed and bounded interval. So can you see that, okay, we've got an issue here. All right. So the way that we're going to fix it, is we are going to adjust such questions. We're going to make adjustments to such questions so that we're going to compute, in fact, we're going to cut off most of the shape and then just integrate a small part, a part that, in fact, you can draw a circle around. So like, you know, like this pointy bit goes all the way to the right, but if I just cut it right there and say, nah, I'm going to ignore all that stuff and just look at that bit, do you observe I can draw a circle around it? That means that it would be permitted that we integrate that part. Similarly, concerning this, you know, it's pointy all the way up. If I cut it, say, right there, so that that's all that we see, do you observe I can draw a circle around that? Then it is permitted that we should integrate that. Okay? So finally, to sort of describe to you why we have to do this sort of circumlocution is something like this. So please consider. Suppose that we all go into business, and we are in the hotel business. And we have a hotel, and it's got 4 rooms in it. And at the present time, 3 of the rooms are filled with red people, I guess, because I'm drawing them in red. So then now suppose that a green person shows up, and they ask, you know, can I have a room? What's the answer? The answer is yes. Go right ahead. So yeah, sure, green person, go ahead. And then now suppose that blue person shows up, and you ask, and they ask, can I have a room? Now what's the answer? No. No. The answer is no, because, you know, we're not willing to share or whatever. Okay? We're full now. All right. What if, since we're in a math class and we have a hotel, suppose that we have a hotel that instead of having 4 rooms, in fact, it has infinitely many rooms. Okay? So it has infinitely many. It has a room number 1. It has a room number 1,000,000. It has a room number million. It's got them all there. And suppose that every room except the first room is full with infinitely many red people. Okay, so red people all the way down the line. And then a green person shows up and says, can I have a room? What's the answer? Yeah, go ahead, go into room 1. There you go. And so now at this time, in fact, every room is full. And then blue person shows up and says, can I have a room? Now what's the answer? Yes. The answer is yes. How could that possibly be right? They're all full. All right. So we'd say, okay, I just get on the loudspeaker and say, everybody needs to move down one room. Everybody moves down one room. And now the new state of the hotel is this. Blue person is in the first room. Green person is in the second room. And all the other rooms have infinitely many people in it. Or have red people. Okay? So this is just a neat little demonstration to show you that when infinitely many things, items are involved, really strange things can occur. If you have 4 slots, 4 boxes, and they're all full, and it's only permitted that you should have one item in each box, and there is an item in each box, then you can take no more items. You can't do it. But if you have infinitely many boxes and they're all full, can you fit another one? Sure you can. You just shift them. And there's all kinds of crazy stuff after that. Now, the thing is that, remember, an integral is cutting a shape into infinitely many infinitesimal pieces. So there's an infinite thing there. And then what we're going to do is we're going to truncate those shapes into smaller shapes and perform an integral. And understand that means an infinite operation. Then after we do that infinite operation, we're going to do a second infinite operation. So that one followed by another. And it is necessary that you must do them in that order. So this infinite operation and then that infinite operation, and it is not permitted for you to do them in the other order. Okay. So concerning that, I could say, for example, please evaluate this. Say the integral from, how about 4 to infinity of, say, I don't know, 8 over x squared dx. Okay, so the question is that, in the first place, sketch what this means. Sketch what that would mean, and then once you've done that, I want you to truncate and evaluate, and I'll show you what that means. And then 3, I want you to compute the limit, and you'll see what that means. So, as for 1, so you must know, okay, you have to know what 8 over x squared has to look like. And in particular, we're only interested in it from 4 to infinity. So drawing that is going to look like this. You know, something like that. So that is the plot of y is 8 over x squared. And this integral means what with respect to this plot here? It's all this stuff, right? From 4, it's this green. From 4, and then how far to the right does it extend? Now, because that shape goes all the way to the right, that means that this integral is not proper. That's what it means. Or, if you like, it is improper. So not proper because the shape is unbounded. All right. So we need to fix it. So truncate and evaluate. So now, what I mean is that okay, I'll take this shape. And here's 4. And what I want you to imagine is that I'm going to just come over here with my scissors and just clip. I'm going to clip it just right there. And I need to give a name at the clipping point, and it needs to be a variable. So we can use any variable that you like except x. What do you want to use? What did you say? Lando? Lambda. Oh, lambda. Okay. I was thinking like Star Wars. Lando. Okay, lambda, fine, doesn't matter. So here's some lambda. Okay, I cut right there. Okay, now the shape. So that's still the plot of y is 8 over x squared. But the truncated shape that we're talking about is this. And now do you observe that, in fact, that's a bounded shape? That's a proper shape. So what is the integral that tells you the signed area of that shape? What will it be? Integral 4 to lambda. And then this. Now, you know, to be clear, it must be the case that this lambda is more than 4. Okay. Now, this integral, that's a proper integral. It's proper. Which means that you're now permitted to use all of the stuff that you know. Okay, so now we'll just proceed. So, you know, proceeding, this we've integral 4 to lambda, 8 multiply x exponent negative 2 dx. We can use the power rule. So this would be 8 multiplied by x to negative 1 divided by negative 1, evaluated from 4 to lambda. Making a little bit of simplification. So in the first place, x to negative 1 I'll write as 1 over x. So I could write this as negative an eighth times 1 over x, like this. And for my taste, any time that you're doing the boundary evaluation, but there's a negative right there, I always spend that negative so that I don't have a negative. But what's the cost of spending it? How do we get rid of it? By reversing the boundary order, by saying that this is lambda to 4, like that. So, you know, look carefully what it was that I did. Negative. When it's negative, we were going 4 to lambda, but then I killed the negative by saying, nope, we're going to go lambda to 4. Okay. Then evaluating this, we get an eighth. I'll leave the eighth factored out, and then that'd be a fourth minus 1 over lambda. Any question about this? Yes?
So for that part where 80 is multiplied to x inverse divided by negative 1 before that.
Mm-hmm.
So doesn't 8 stay there?
Oh, my goodness. Somehow I made it, okay. Yes, it should just be an 8. I don't know, I don't have any idea what happened. It should not be a 1/8. Thank you for being courageous enough to speak up, because otherwise I just would have kept going. Okay, so this needs to be, so negative 8, and then this is just regular old 8, and then regular old 8. Okay, good. Now, any questions besides that unintentional mistake I made? All right, so what this represents, this is the area of the proper shape, So it is not the area that we were requested to find. But we can find the area by saying, well, you know, we'd get more nearly to the area that we want if I grabbed this lambda and just moved it over to a little bit. We'd be nearer the true answer, right? And then if I grabbed the lambda and moved it even further to the right, we'd be even nearer the true answer. So conceptually, to get the true answer, we need to take that lambda and we need to move it all the way to the right. How do we do that? Yeah, now we let lambda go to infinity. Let lambda go to infinity. So then we'll calculate the limit as lambda goes to infinity of that expression there. 8 multiplied by a quarter minus 1 over lambda. So what's the limit of 8? It's 8, right? What's the limit of a fourth? A fourth. And what's the limit of 1 over lambda as lambda goes to infinity? It's 0, right? Because lambda is getting arbitrarily big. So 1 over lambda is going to go to 0. So this is 8 multiplied by a quarter minus 0. So if you like, 2. That's the answer. Huh. So what that's saying is that, you know, if you had a shape like that, and if we were measuring in, you know, American units, you know, it might be like 2 gallons. That's how much paint it would take to do it. 2 gallons. All right, good. So I just want to mention, because we've got just 30 seconds, there's another way in which this can be improper. So an example is something like this. Integral, say, of integral from 0 to 3 of the logarithm of x dx. Now, at first blush, at first glance, it doesn't seem like, you know, this integral might seem to be a perfectly legitimate thing. Might seem to be okay. Because after all, the other one was kind of obvious, right? The fact that the infinity was staring you in the face, that's telling you something's at issue. But nevertheless, this one is just as improper. And then once I draw this, I want you to think about how you could fix it over the weekend. So the x-intercept of logarithm is right there at 1. When you plot logarithm, away from 1, you go like that. And then when you go towards 0, what does it do? It goes down, right? Like this. In fact, all the way down, right? So if I plot 3, 3 is like over here, then what's being requested is this shape. So we've got this much, but we also have this much. And how far down does that shape go? All the way down, right? You can't put a circle around it. So how could you fix it? Well, you cut right here at a point that you might call something like A. And then instead of integrating from 0 to 3, you integrate from A to 3. Because if you cut it at A, then now that's a bounded shape. So integrate A to 3. And then you do that. And when you do that, you'll have an expression that depends on A, just like this expression depended on lambda. Once you have that, then what do you do with that? You let A go to, not infinity, to 0, right? 0 is the problem. So you cut right there, and then you say, okay, now I'm going to move A over to 0. Whoop. All right, and we'll do another one next time. Have a nice weekend.